I hit the button.
Okay, so my Southie people, you all will get this tomorrow. But, so this is the sheet for AP Physics 1. So let me kind of explain what this is. So we're going to go through eventually all of these equations. It kind of lays out what the equations are, and then over on the right side, it explains what the variables represent. So, and then on the back side, you've got your prefixes. The only ones we'll use mostly, at least in the fall, is going to be kilo, centa, milli. Once we get into the spring in AP Physics 2, we'll deal with like either the extremes on the very big side or the extremes on the very small side. So what we're going to deal with most are the three right in the middle, kilo, centa, milli. So what will happen, like when you all take tests, I will give you a laminated version of this. So this is what you will be able to use on the test. So this is yours, keep it handy. Once we get into AP Physics 2 in the spring, you will have another that's going to be on, that's a purple sheet that you will have for that part of it then. So for now, this is going to become your bread and butter. Find some way to keep it neat and handy, okay? Not shoved into a backpack, wadded up in the bottom of, I'm just saying. You actually have a notebook?
I actually have a notebook.
Okay, this would be a cool thing to keep handy.
I'm actually really good with keeping laminated versions of information. So I have my own from AP Bio, and I have my periodic table from Chem.
Okay. All right.
But this isn't laminated, so it will die.
You want a laminated version of it?
Yes.
Yes.
I'm not going to write on it, so a laminated version will result in me thinking it's important and keeping track of it. I'll trade you. Merry Christmas.
Thank you.
Laminated, or are you good with paper?
I don't care. I keep my stuff neat.
Okay. Will's going, not to be a snob, but, okay. All right. Okay. So, now, so, the lecture notes that I gave you, all right? So, like I said, you're all gonna have a textbook by like the important stuff. I will generally just give you like a summary sheet going, hey, here's the things that you need to know. So, first thing we need to figure out is what units are we gonna use to measure stuff, okay? And that's fundamentally what you're gonna do. So, there's two things that you struggle with in the realm of science, especially with physics. One is coming up with a mathematical way to describe it. The equation that says, hey, this is how long it should take, this is how much force there is on the surface, this is the mass, whatever that is. So you got the equations. The other part of that is how do you measure it? How do you measure time from here to here? How do you measure the mass of the moon? How do you measure the mass of a proton on the other extreme, or the mass of an electron? How do you find the mass of something so incredibly small? Because it isn't like we can take a pair of tweezers and grab an electron out of the air and put it on the scale and go, oh, there's the mass of the electron, okay?
Dang
Can't
it.
do it. We can't stop Jupiter in its orbit and, oh, we'll just grab Jupiter and put it on a scale and go, oh, here's the mass of Jupiter, okay? Measuring the mass of a black hole, measuring the diameter of a Milky Way galaxy.
But have we tried?
To do what?
Grab Jupiter, put it on a scale. Maybe we should
Probably
just
not
try
so
a little
much.
harder.
No, a little bit tough to do. Has a lot of momentum.
Maybe in the future.
And it would be a really, and not to mention the fact that it's a gaseous planet, so it really would do well to try and put it on the scale. So, I'm just saying, just throwing that out.
Jupiter's oozing off the scale again.
Yeah, well, the weird thing about Saturn, if you put Saturn in water, Saturn actually would float. Because Saturn overall is less dense than water. So Saturn would float in the bathtub, let's say.
So I should chill my drink by floating a Saturn in it, is what I'm hearing?
No, that's not what I'm saying at all. I'm just saying it would float. That doesn't mean it's cold. It's just would float.
Saturn isn't cold?
Depends on which part of Saturn that you're on. So, whole nother story. Whole nother story. Focus, guys. All right. So, what physicists had to figure out is that what units are we going to use to measure things in? So, are we going to use inches? Are we going to use pounds? Are we going to use grams? Are we going to use kilograms? So, when you look at the history of science, and we've screwed some things up along the way, and that was one of the big things, is like, what are we going to use? So they finally decided, hey, let's settle on physics. They're going to use what's known as the MKS system. So the M is going to be, don't be this way. There we go. So meter stick about yay long, not a big deal. And so even if you look at kind of the history of how they developed the length of the meter, it took the distance, the circumference of the Earth going through the prime meridian in Greenwich, England, and they said, here's the distance all the way around, and they subdivided it, and they said, okay, this is what we're going to call a meter. So when you look on your equation sheet, so when you look at like a distance, typically on your equation sheet, that's going to be represented by the letter X. Sometimes you'll see it written as D. So if you're talking about a vertical distance, we might represent it as Y. If you're talking about a length, it might be shown as the letter L. Okay? So, and that, oddly enough, is going to be M. So if you see, boom, 5 meters, not a big deal, easy peasy, not a problem. Now, kilograms becomes a little bit more problematic. Okay? So when you look at kilograms, which is kg, so when you look at kilograms, kilograms is a measure of mass. So let's begin to clarify a couple of things right away. So when you look at a 1 kilogram mass, which is about 2.2 pounds. So mass, unless you're under extreme situations of very, very strong gravitational fields, where Einstein's theory of relativity becomes a factor, which we're not going to have to worry about, mass stays the same. So, and this is a horribly non-scientific explanation of mass, but stay with me. So mass is a measure of the amount of stuff that's inside of an object, okay? I said it's non-scientific, but it works, okay? So if I take this copper tube, which has a certain amount of mass, because it has a certain amount of stuff, and I take it to the moon, this thing is going to have the exact same mass on the moon as it does here. If I go to Saturn, okay, wherever I go, this thing is going to have the same amount of mass. Now, where it gets weird is when you get into talking about what something weighs, which is a measure of force, okay? So weight is dependent upon gravitational field. We're going to spend a lot more time talking about this. I'm just beginning to lay the framework of this. So when I talk about mass, it's a measure of stuff, okay? That's it, it's a measure of stuff. How that stuff interacts with the gravitational field is a measure of weight, okay? So mass is stuff, weight is an interaction with the gravitational field. So this is where this gets a little bit confusing. So when you see kilograms and mass, that's represented by the letter M. So here's where I want you to begin to, what you have to watch a little bit, is that when you look at that big sign that's hanging back there that says F equals MA, that M is in kilograms. So let's say you have a 1 kilogram mass, and you're going to make it accelerate, not decelerate, at 2 meters per second squared. Then that would be 2 kilograms meters per second squared, or 2 newtons, okay? So when you look at the accelerator, and you're going, what is 2 meters per second squared? Is that fast or is that slow? So the gravitational acceleration on Earth is about 10 meters per second squared. Typically, like when you press down on the gas pedal of your car, unless a typical average acceleration of a car is around 2 to 5 meters per second squared, okay? Like you would really have to press down on the gas pedal to really get an acceleration of like 7 to 8 meters per second squared, okay? So 2 meters per second squared isn't all that much. So if you look at this range of rock that we're on, okay? So we have a gravitational field. So if you look at all the things, that got loud, that had to happen for us to be sitting here in room G20 on August 15th at 9:20 or 8:40 in the morning, one of the things that we have to have is we have to have an atmosphere. Okay, if you don't have an atmosphere, then we're not here because you can't breathe, you don't have weather, you don't have rain, you can't grow crops. So on a relative scale, if the Earth was an apple, okay, and you cut that apple in half, and you look at that thin skin of the apple, that's relatively the size of our atmosphere, okay? That's it. So if the Earth is the size of an apple, we exist because a layer of gas is around us, the thickness of that peel. Okay, that's it. We have a strong enough gravitational field to hold that atmosphere. Mars doesn't have an atmosphere. The moon doesn't have an atmosphere because they don't have a strong enough gravitational field to hold one. So one of the things that's convenient for us is that we have a strong enough gravitational field that we can keep an atmosphere. We spin at a certain rate. It takes us about 24 hours to spin on our axis. That's cool. Even that rate of spin is important because if we spun faster, number one, the days would be shorter. Number two, storms and wind would become much more severe, which would be detrimental to our existence. If the Earth was spinning much slower, that would also impact us in terms of heating and cooling. So if we were spinning faster, the days would be longer, and you would have more extreme warming in the day. And at night, you would have longer nights, you would have more extreme cooling at night. So we're tilted on an axis, okay, about 23.5 degrees. So that allows us to have seasons. If the Earth wasn't tilted on its axis and we were like this as we went around the sun, and it was exactly split, like if the plane of that spin was at an exact 90-degree angle to the light that comes from the sun, we wouldn't have seasons. If we were tilted too far, our seasons would become too extreme for us to be here having this conversation. So if you look at the distance from the sun, we're in what's called the Goldilocks zone. If we were closer to the sun, we'd be too warm, and the oceans would evaporate, and we'd be a hot rock, basically, okay? If we were further away, we'd be too cold, and we'd be an ice cube, and the Earth would be covered with ice. So there's a whole bunch of things that have to happen conveniently to work out for us to be here. Now, people have asked me, like, what do you consider the coolest part of science? Here's my answer. We have gravity. So if you look at what happened with the Big Bang about 14.8 billion years ago, give or take about 5 minutes, something happened. We don't know what. An event happened, the universe came into existence. And then out of that morass, the universe began to cool. And matter began to form out of energy. And you got protons, neutrons, and electrons. And conveniently, our universe has gravity. Cool. Because if we didn't have gravity, we wouldn't be here having this discussion. So a very short version of the history of the universe is that you began to see fluctuations in the gravitational field. Mass creates gravity. So then that hydrogen began to stick together, began to get clumpy. Okay, the universe began to clump together. And you had the first generations of stars. So if you look at what elements existed right after the Big Bang, it was basically hydrogen. You had maybe a tiny bit of helium, maybe a tiny bit of lithium, but basically it was hydrogen. So if you look at what had to happen, so that first generations of stars formed, and then you began to see it would be cool to watch. So you would begin, if you were an outside watching in, you would see flashes of light begin to appear. Oh, there's a star that just got started. Oh, there's another star that fired up. And that takes tremendous heat and tremendous pressure to fuse hydrogen into helium because they don't like each other. The two protons don't like each other, so it takes tremendous pressure and heat to force them together. So then those elements, that hydrogen began to coalesce in the fusion process to produce helium. And then those stars exploded, okay? And out of that explosion, then that's when you began to form the heavier elements, the carbon, nitrogen, oxygen, iron. So up to about, through the element iron on the periodic table, all of those elements had to form in the deaths of generations of stars. So it's an old cliche, but as human beings, we are all made of stardust. So all the complex atoms that make up all of you, the nitrogen, the oxygen, the carbon, that allows us to have an atmosphere, that allows us to exist, none of those atoms existed at the beginning of the universe. They all had to be formed. And then they just weren't formed in a factory, they were formed in the collapse of stars. It was very violent. All those atoms got kicked out into the universe, and then they got recycled, and then they began to form again. So odds are, and I don't know, you'd have to be pretty born to do this calculation, but if you look at the atoms that make up the right hand, odds are those atoms here came from a different star that make up your left hand, okay? Even all of those atoms didn't come from the same star. So if you look at everything that had to happen for us to be here having this conversation, it's a pretty cool sequence. So if you look at gravity, okay, we talked about gravity. If gravity was stronger, we wouldn't be here having this conversation because of the fact that the universe couldn't have expanded. If gravity was weaker, we wouldn't be here having this conversation because you wouldn't have enough gravitational pull to make the first generations of stars begin to form. So there's a whole bunch of things that had to happen for us to be here. And people, and I've reached the point, I'll be 58 here before too long. And it's like people ask like, hey, Burkamp, when are you retired yet? I'm to the point now when I see my former students, are you still teaching? It's like, do I have a walker? No. It's like, I'm that old. But the reason that I'm still teaching and the interactions that I love with my students is that the more you study science, it's just cool. I get to teach what I believe is like the coolest subject of all. It's like, we get to teach about how the universe came to be. That's pretty cool, So when I first went to K-State, I actually studied a lot of math. And I thought, I'll be a math teacher, but I also took some chemistry and physics. And then, the more you study math, I was like, okay, teaching math, it's important, don't get me wrong. We can't do physics without math. But teaching math is kind of boring, okay? Oh, let's talk about the quadratic equation today, kids. There's no way to make that exciting, okay? There isn't. There just isn't. So I get to teach a math class that we call physics and chemistry, okay? And so that's basically how I view this. This is a math class. But I can go to Dr. Botts, who I've known since he was 8 years old. And I can go to him and go, hey, I need a remote control helicopter. Why? Oh, we're talking about forces. Oh, okay, go buy a remote control helicopter. So, or I need a bed of nails, or I need a roller coaster, or whatever. And I was like, why? It's physics. Okay, cool. So I get to teach math. No, it's a true story. So I get to teach math with exceptionally cool toys. And that's fundamentally what I do. And so, when people ask me, so you still teaching? Like, yeah, still am. So there you go. So, the last of these to get through this today. So you have the MKS system. S is going to be time, that's going to be seconds, okay? So those are the three fundamental units. And from that, and we'll talk more about this tomorrow, you can get velocity. And there's a whole bunch of different ways to calculate velocity. One is distance divided by time. Now, you're going to hear me preach this again and 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 again. And that's the importance of understanding science as a process. Okay? It isn't just getting an answer. And so, if there was one wish I had for all of you, is that you immediately understand that when we do problems, I'm going to do a lot of problems in this class, is that when you hand in a paper, and for your first 12 years of education, however that is, teachers have emphasized, did you get the correct answer? Did you pick C? And now it's like, did you go onto the computer program and did you type in the correct answer of 5.0? Okay? And that's all you're worried about, is that did you type in the correct answer? And yes, I'm old school, and I'm very much concerned about that process. So the sooner that you view physics and any advanced science as a process, and just not the product as the answer, the better off you're going to be. And there's parts of this process, and one of them is, hey, what are the units? Because up to this point, especially now that they've shifted towards like the computer-based homework, you just have to type in 5.0. It's a number, doesn't have anything. But here's the problem in a physics class. If you just write down an answer of 5.0, I have no idea what that means. Is it 5.0 meters per second? Is it 5.0 squirrels? Is it 5.0 times the mass of the sun? I don't know.
5.1 squirrels.
Yeah,
We don't ask what happened
0.1
to
squirrels.
We don't ask what happened to the other
Maybe you just have like
0.9 of a
potato.
squirrel.
I don't know.
Go
But,
take a
yeah,
nice bite out of
rounding
it.
with squirrels is tough.
So we should round to the nearest squirrel?
Round to the nearest squirrel.
Good to know.
Probably round up or down, depending on your reference. So,
More squirrels.
but here's the point. So when you look at, hey, what's velocity measured in? And there's a whole bunch of different ways to calculate velocity. But one of them is that you take, let's say, for example, we just got done with the Olympics. Okay, they ran the 100-meter dash. And they did that in about 10 seconds. Okay, so if I take 100 meters and divide that by 10, they ran at about 10 meters per second. Okay? Now, did anybody see the 100-meter dash? The difference in the times, how much the guy won by?
Yeah.
Or was it like 5,000ths of a second?
Yeah.
Okay? So, obviously, if you're going to measure, and we'll get into precision and accuracy, if you were just standing there with a stopwatch going boom, and then you had the guy at the end going stop, okay? And they could only measure to the nearest tenth of a second, they'd probably just call it a tie. But because they had the technology to measure to the thousandths of place, that's what allowed them to make that difference. So when you look at how we measure things, it's how well can we measure them, and then what can we do with that? So if I just write, we'll talk about significant digits later, but if I say, hey, how fast did they run? 10 meters per second, and I just write it as 10, I'm going, close, it's an estimate. They ran about 100 meters, it took about 10 seconds. Now, if I say they ran 10.05 meters per second, that conveys a completely different level of precision. So there's a huge difference between going, how fast did they run? About 10 meters per second. Versus how fast did they run? 10.05 meters per second. Big difference between those two. So when you write down mathematical answers in this class, and you're gonna write down a lot of them, you have two decisions that you have to make if you think about it. How many digits are you gonna write down? And what units are you gonna put on the end of it? And they both convey information. The number of digits convey how well your data is, how good is your data. And the units tell me, hey, this is what we are measuring. Okay, so we're gonna stop here. Your quote homework for tomorrow is to read through that sheet of lecture notes that I gave you. May South people, I will just give you all this tomorrow, or send you this link on YouTube, and we're off. So, call it a day. Tomorrow